Okay, that's great. Yeah, so thanks very much, everyone, for coming, and thanks very much to Jacob for the invitation to speak. Yeah, it's really great to be here. So this project is kind of a follow-up to a paper I wrote a couple of years ago, and that paper. So this is part of kind of a broader project of looking at intrinsic presentations of physics. So the motivation, perhaps even more strongly for that earlier project, was motivated by some reflections on the structure of quantity. So these reflections aren't new to me, obviously, but yeah, this is kind of the starting point. So the thought is, observation one, we typically use numbers to represent physical quantities. Quantities here, not going to be defined super rigorously or strictly, but mass, length, duration, density, volume, electrical charge, so on and so forth. But there's, obviously a certain amount of representational redundancy in the way we go about doing that. What do I mean by that? I mean that the real numbers, in some sense, have more structure than the quantities that we're using them to represent. And the way that kind of manifests is in the fact that there's a certain amount of conventional choice or conventional freedom that we have in setting up this representational relationship. So I might have some particular mass, and I could represent that by the number 5, perhaps if I'm using the kilogram convention, or I could represent it by 11 if I'm using the pounds convention. And so the idea is then that that is, if we think that the structure of the real numbers has sort of excess structure above and beyond the structure of all possible values of mass, then that sort of motivates us to look for an intrinsic kind of formulation, one that characterizes what the space of possible mass values is like in a more intrinsic way, and that does away with that kind of excess or surplus structure. I mean, I should say this is very closely related, obviously, to Field's program. It ends up being slightly different, basically because I don't really have the kind of nominalist motivation that Field has. And so I'm going to be very happy to have things like bases of possible mass values that Field suggests he's not so comfortable with. But there are going to be, there's I think at least a kind of nice conceptual connection. And actually Eddie, who I notice is here today, has a nice paper on, in fact, intrinsic quantum mechanics, where he gives, I think, quite a nice discussion of the way in which one can sort of think of Field's program as kind of breaking down into 2 parts, really. There's kind of an intrinsicalist project and a nominalist project really going on in Field in some sense. And so I'm just going to be concerned with the intrinsicalist project in the same way that Eddie is. And the relationship between what I'm doing here and Eddie's work is something that I may talk about briefly at the end, but otherwise it's something that I'm sure we can talk about in Q&A. Good. So, right, so this is just kind of what I've already said, that I've started looking at this kind of project earlier. So in that paper, I sketched in broad terms how to do physics in a kind of unit-free way for classical Newtonian gravitation and classical, not really electromagnetism, actually, more just, I think it was actually just electrostatics now I think about it. So, sorry, a little bit of an overstatement there. But then, right, so part of what I want to do now is think about how to extend this to quantum mechanics. And part of the reason I think it's interesting to do that is partly just that quantum mechanics is at least more true than either gravitation or electrostatics. But there's also kind of a couple of features of quantum mechanics that maybe make it particularly interesting. So one, so I mentioned already this connection to Field's program, and kind of famously, David Malaman challenges Field on how his program could possibly be extended to quantum mechanics. I mean, part of that, I think, is arising really more from the nominalism than the intrinsicalism, but it suggests that like the extension to quantum mechanics, may not be totally trivial. The other thing that I think is interesting is that I've been bothered for quite a while now about the way in which, on standard versions of quantum mechanics, we identify the values of quantities with the eigenvalues of the operators associated to those quantities. And there's something a little bit odd about that if you think about it, because it's kind of hard to see how eigenvalues could fail to be anything but numbers. Whereas, and it's kind of hard to think about what it would mean to have an eigenvalue that was just a point in a three-dimensional space, for example. So those are kind of motivations for starting to think about this. I should, I guess, probably just confess at this point that I don't, I think, have really resolutions of either of these two issues with the project as it stands. But these are kind of motivating, and so I'm hoping that when I do actually get to kind of the finished version of this project, I'll have something a bit more insightful to say. So this is still, I'm afraid, work in progress, and so I'm particularly interested in suggestions for how I kind of get from where I am today to a point where I can potentially say interesting things about these two issues.
Neil, I'm sorry to interrupt. Can you hear me for a second?
Yeah.
Yes. There's a strange blinking going on in our view of your screen. It seems to be coming from the toolbar at the top. Is there a way to, yeah, that looks much better. Okay, I think that'll fix it.
Weird.
Thanks, sir.
Okay.
Sorry about that.
Right. Yeah, no idea what I was doing now. Sorry. Yeah, thanks. Good. So
it's returned.
So
yeah. Every time the toolbar appears, we start seeing this blinking. Is there a way to suppress the toolbar permanently?
So I can't see the toolbar on my screen, slightly bizarrely. I mean, is the toolbar on your screen?
It's now gone. It just occasionally seems to reappear and then it blinks. Okay. Well, I don't want to interrupt. You should just continue going.
Yeah, let's carry on. I hope it's not too annoying. So good. Right. So here's what I'm going to do today. I'm going to start with just an introduction to how I'm thinking about scalar quantities, kind of basically in the classical case, because that'll lay out a lot of so that'll rehash some stuff that I've done before, but lay a lot of the groundwork that we need for this case. Then I want to talk about the idea of complex scalar quantities, kind of sketch why I think those are needed, and then use that to give a version of a Hilbert space that doesn't have this kind of, doesn't have a certain amount of surplus structure. So let's press on, let's see how that goes. So so here's the basic motivation for the picture of scalar quantities that I want to present. So I've already touched on this idea that a manifestation of the fact that scalar quantities don't have the same amount of structure as the real numbers is that we have this sort of kind of conventional choice whether you use kilograms or pounds. But here's something which is not conventional. Is the ratios between two values of that quantity. So the fact that one mass is twice as heavy as another is something that's going to hold regardless of what system of units we choose. And so it's a unit independent. So this is kind of, as it were, a place where real numbers can come in perfectly legitimately. So real numbers as codifying ratios are kind of completely fine. And so what I want to do is think about a way to encode scalar quantities as structures that are defined by such ratios. And so we're going to have a few different types of scalar quantities, although actually now I think about it, I think I'll mostly be using positive scalar quantities, so I'm not going to have to worry too much about. We'll come back to this. So I mean, the motivation here is to say, okay, if the characteristic thing about say the space of all possible masses is the ratios between those masses, then I mean one way to think about what's going on there is that we might think, well, perhaps the structure of that space of possible mass values is entirely coded up in the facts of the form for a given value of mass and a given other value of mass. The ratio between those two values is such and such, is 2 or 3 or whatever. So what that looks like is that you want to say, well, look, for any two mass values, there's going to be a real number, which is their ratio. Moreover, I'm going to kind of require that those ratios play with one another in the way that I want. So if B is twice as massive as A and C is 3 times as massive as B, then it better be the case that C is 6 times, as massive as A. What that ends up kind of getting coded up as is that we expect that the scalar quantity should be a principal homogeneous space with a multiplicative group of positive real numbers. So to remind you, so a group action of this multiplicative group is just an association of real numbers with with bijections on, let's say, the space of all possible masses. So each real number is associated with a certain bijection. And if I do two of those bijections in turn, associated to two different real numbers, then the result of composing those two bijections is going to correspond to the product of those two numbers. So that's kind of roughly the idea. And then the fact that it's a principal homogeneous space just means that this action has to be free and transitive, which means that for any two numbers, there is a unique real number such that the one is the image of the other under the bijection associated to that real number. Okay, and so that's what delivers us this idea that for any two values, there's a unique real number, which is their ratio. And so examples of quantities like this would be things like mass or length. Good. Oh, the other thing that maybe is worth mentioning here is that a general feature of our principal homogeneous spaces is that they're often characterized or described as being like the group, except the group of which they are the principal homogeneous space, except without the choice of a unit. So it's like take the multiplicative group of real numbers, and then, as it were, forget the identity of that group, i.e., in this case, the number one, and kind of all the information from which you could deduce that. So that's kind of another way of thinking about what a principal homogeneous space is. Anyway, so that's going to give us positive scalar quantities like mass or length. But there are other kinds of scalar quantities. So roughly speaking, as it were, some scalar quantities very roughly take both positive and negative values, or would be represented by like the full real line, not just by the positive real numbers. So we want to be dealing with a full scalar quantity, then quantities like that we'll characterize as being a one-dimensional real vector space. So what that means is that, I'm going to assume that you all know what a real vector space is. I'll also note that I'll sometimes talk about quantities of this kind being signed or unsigned. So it's signed if it carries an orientation, it's unsigned if it's not. So any quantity like this has, as it were, two halves, right? So we have the half here and the half here. If you stick on an orientation, then, in rough terms, that means that there's like some kind of intrinsic difference between this half and this half. Slightly more formally, we no longer regard multiplication by -1 or multiplication, in fact, by any negative real number as being an isomorphism of the structure here. So, examples, I would say that electrical charge, at least in classical electromagnetism, is unsigned because, for all that we label certain kinds of things positive and certain kinds of charge negative, the theory would work just as well with the other, doing it the other way around. We have a kind of conventional choice about what kind of charge to label as positive or negative, at least in that theory. By contrast, if you think that time has an intrinsic direction, then you're going to think that temporal displacement is signed. There's a difference between future pointing temporal displacements and past pointing temporal displacements that's kind of intrinsic to those displacements and isn't mere conventional choice. Good. I think in the interest of time, I might skip this. This is just to note that, if you want to make the connection between positive scalar quantities and full scalar quantities a little more vivid, then you can do that by noting that positive scalar quantities are semivector spaces rather than just vector spaces like full scalar quantities. So there's like a bit of like technical stuff about how you do that, but that kind of just, I think, makes the relationship between the two kinds of scalar quantity a little more apparent. Good. Now, of course, one thing, it's not enough to just have then intrinsic scalar quantities like mass or length or whatever. We also want to be able to kind of do algebra with those quantities. We want to be able to, for example, multiply a mass by a length or multiply a mass by a speed. And so what that means is that we need a way of, so in particular, one of the bits of structure that we lose by getting rid of the real numbers is that we're no longer allowed to just multiply, say, two masses together to get something that lives in that same space, okay? So, when you're using the real numbers, of course, you can just multiply two real numbers together, get another real number. That's great. If we multiply two mass values together, then we don't get another mass value, which, makes sense, right? We don't expect to get a mass value, we expect to get the square of a mass. And so we need some way of kind of making sense of this idea. So this is what I'm going to kind of quickly sketch now is how to develop these new scalar quantities. I'll write the scalar quantity that is where products of values of A and values of B live as A tensor product B. Hopefully it'll kind of become clear in a moment why that is. Well, in fact, yeah, I'll just call it a tensor product because it is essentially. So here's how we do this for, right. So here's just kind of how you go about doing it. So take some element A of, some element small a of big A, and take some element small b of big B. And then an element of the product quantity is going to be just something of the form small a tensor small b. I'll just kind of write it as that. But I'm going to impose this condition that if I that xa tensor b is going to be regarded as equal to a tensor xb. So what's going on in the background here is I'm really taking a and b, I'm forming their Cartesian product. So you can imagine, so suppose a and b are positive scalar quantities. So I take those two quantities, I form their Cartesian product, which is this whole kind of two-dimensional thing. And then I take a quotient. So this condition here is basically instructing me to quotient that Cartesian product by a certain equivalence relation. And what I'm going to get are surfaces, as it were, that look like this. So these will correspond to a single value of the product quantity, a tensor b. And so, yeah, the whole quantity, as it were, you can think of as consisting of all of these individual sheets. Now, so that sort of defines the set of things. I now, so let's just continue thinking about the case of a positive scalar quantity. I now equip this set with an action of the positive real numbers. I do that by just saying, well, look, if you act on it with, so if you act on this thing a tensor b with x, you get xa tensor b. That is equivalently a tensor xb. So I just let it act on either coordinate that defines an action on the whole thing. It's pretty easy to check that. So if a and b are two positives, well, right. So that will give me an action of, yeah, that'll give me an action. Using that action, I can then, as it were, figure out what kind of structure I'm dealing with. So, for example, if I take two positive scalar quantities and I cook up this tensor product and I define the action of the positive real numbers, as I mentioned a moment ago, one can show that that action is free and transitive. So what I've got is a positive scalar quantity. So this is what this first equation is supposed to kind of suggest. Start with two positive scalar quantities, and you'll their tensor product will be another positive scalar quantity. But if you take this prescription, nothing in here really depends on the condition that I must be dealing with positive scalar quantities. So I can also think about what happens if I multiply together positive scalar quantities with full scalar quantities. So that if I do this here, then I end up getting I will get another full scalar quantity. And if I multiply together two full scalar quantities, then I get another full scalar quantity. Also, if I've got some signs around, so if I take if I take a positive scalar quantity together with a full scalar quantity with a sign on it, then I also get the result is also signed because I regard basically the result of multiplying any positive element of this by some element of the positive scalar quantity as itself positive, and any negative element of the full quantity by any element of the positive scalar quantity as also being negative. Similarly, if both of my original full scalar quantities are signed, then the result and product will also be signed. So I just, again, so I do that in the obvious kind of way. I say, well, look, if you take the product for two positive unit elements, you get something positive. Two negative elements also gives you positive, and a positive and a negative, or a negative and a positive, gives you a negative. Good. Okay, so that's how to then do, as it were, a multiplication of scalar quantities by one another. It's also going to be helpful only fairly briefly in what's to come, but it is going to show up that we want to be able to take powers of these kinds of quantities. So the way you do this, so this actually is based on a math overflow answer by Theo Johnson Frade. So due credit, commenting on a blog post from Terence Tao, is where I kind of picked up this, how to do this. So what we're going to do is, I'll just describe it for positive scalar quantities because that's the simplest case. I haven't totally figured out what this looks like for full scalar quantities yet. So what you do is you just take your positive scalar quantity P, and then take any real number R, positive or negative, rational or irrational. And you, so I'm going to say that its power, P to the R, just consists of elements of the form small p to the r. Okay. So small p here is an element of the positive scalar quantity p. That's obviously kind of purely formal, right? So sort of purely formal characterization of this set, big P to the r. But I'm now going to give that some structure. So I'll say that's a positive scalar quantity. I need to define an action of the positive real numbers on it. I do that by saying, well, look, for any positive real number x, xp to the power of r is equal to x to the r acting on the corresponding element p to the r. So just to kind of see what that looks like. So suppose I start out with my positive scalar quantity p. We've got facts of the form. This is some arbitrary element p. This is 2p. It is obviously twice p. So p squared basically consists of things that I can write in the form p squared. So I have the word p squared here, 2p all squared, which can equivalently be written 4p squared. Why is that? Well, because I've applied my rule for how the action of r plus on p gets associated with it, or generates an action of r plus on p squared. So you can think of this as, we have effectively a map, what's in fact going to be a bijection, mapping each of these guys here to a corresponding value of p squared. Perhaps slightly more interesting. Oh, and then if you wanted to do, say, p to the half, it's basically going to look like this in reverse. So as though you start with this thing here. If you had two elements with a ratio of 4, those are going to, then you're going to map everything upwards. And if you had a ratio of 4 between two elements on here, you're going to now have a ratio of 2. Slightly more interestingly, although isn't going to be super important going forwards, but just to mention, you can also do it, as I say, with negative powers. So there, what was a ratio of 2 now gets converted to a ratio of a half in the corresponding thing. And so here again, we kind of map the elements of p onto the elements of p to the negative 1. This mapping is not order preserving, unlike the either of the mappings I mentioned a moment ago. What's nice about this, of course, is that you kind of need to be able to make sense of negative powers in order to think about not just product quantities like momentum, but ratio quantities like density, for example. So density is a ratio of mass to a volume. The way that's going to come out is you're going to take your length, take length, tensor product, length, or in fact, could also equivalently just take L cubed. But then you're actually going to need L to the negative 3. And so we're going to think of density as living in mass, tensor product, length to the negative 3. So this kind of gives us an apparatus for doing that as well. Good. So it looks like I've actually, okay, this section heading may be wrong. I think this probably should say complex scalar quantities. But that's kind of a brief sketch of how we're thinking about real scalar quantities on this kind of approach. But we want to do quantum mechanics, we want to take advantage of complex structure. And so now I want to think a little bit about how to do the same thing, but for complex scalar quantities. And so the motivation here, again, actually, I'm kind of taking my motivation here from the paper of Eddy's. The motivation is the observation that when we represent things like wave functions or quantum states, they're invariant under, or the physical meaning supposed to be invariant under complex multiplication. So if we have a wave function psi and a wave function z psi for some arbitrary complex number z, we think of these as being physically equivalent. And so what we might want is a kind of multiplication invariant version of the complex numbers. So I should be a little bit, I should maybe just say here, when I talk about a multiplication invariant version of the complex numbers, I don't mean a version of the complex numbers where z and z multiplied by some complex number are identified with one another. That's clearly going to be basically trivial. It'll be, it's just like the two element set. What I in fact want is a version of the complex numbers which such that for any complex number, multiplying by that complex number is an isomorphism of the structure. So it's not that the structure is kind of invariant under it, it's more that it's isomorphic under it. That's kind of, so yeah, that's the motivation, that's the target. Turns out to actually be pretty easy to do this. I spent a weird amount of time trying to think about how to do this and then realized it was much more straightforward. Making my life a lot more difficult than I thought. So the answer is that you should take your multiplication invariant version of the complex numbers to just be a one-dimensional complex vector space. And so I'll say that a complex scalar quantity is then a one-dimensional complex vector space. And in fact, I'll only really need one version of such a quantity. So I'll just call that curly C. Note a nice feature that is sort of useful for various proofs and so on, that if you take that and you remove the zero, then you've got the principal homogeneous space for the multiplicative group of non-zero complex numbers. So any two non-zero elements of this, say A and B, there's a unique complex number which gets you from A to B. You can express in the form RE to the I phi. It'll be what you get by scaling up A by R, and so that it's the same length as B, and rotating it in the Argon plane through an angle phi. Good. And so now we take the kind of apparatus that I was talking about earlier, and we now sort of apply it to the complex case. So say we've got two complex scalar quantities, B and D, then we define a product quantity in exactly the same way that we did for real scalar quantities. So we're just going to say that it consists formally of elements C tensor D, where little c is an element of C and little d is an element of curly D. And but we impose this same kind of condition. So again, we're under the hood taking a quotient of a Cartesian product here. I will just mention, this is also true in the real case, but there wasn't space on that slide. But I'll just take this opportunity to mention that what you get as a result is a complex scalar quantity. And if you take the complex scalar quantity C tensor D, then of course there's a natural way to identify that with D tensor C, namely, any element small c tensor small d is going to be identified with small d tensor small c. Okay, so that's kind of helpful. That's going to be a helpful sort of heuristic. So that's basically then the same as what we had before. Here's something that we can't do with real scalar quantities, is we can't think about conjugates of them. Now, interestingly, one difference of curly C compared to the complex numbers is that you can't conjugate an element of C and get an element of C back again, because it's just a one-dimensional complex space. So there's no identification of some elements of that space as being real or imaginary. And clearly, if you don't have that kind of structure, that kind of decomposition into real and imaginary parts, then you can't do complex conjugation on C itself. What you can do, though, and this is completely standard, is define the conjugate space to C. So that we'll call C bar. This isn't in any way new to me. This is just a very standard piece of complex linear algebra. So this is defined to be a complex vector space whose underlying set is the same as C, or if you want a slightly different way to put it, it's to say that its elements are in bijective correspondence. So any element A of C is going to correspond to an element A bar of C bar. And I define addition and scalar multiplication for C bar according to these definitions. So addition is just is basically the same. So any given element complex number z bar, it's actually slightly more elegant to write it this way. So its action on a bar is the same as letting z, so the conjugate of z bar, act on a, and then taking the conjugate of that whole thing. So this is roughly what this diagram is supposed to illustrate. If I start out with some number a, there's some element of c, a, then there's a corresponding element of c bar, a bar. What's the difference between c and c bar? Well, the action of z on a corresponds in c is to take it to some number z times a. The equivalent action on a bar is equivalent to acting as the conjugate of z, or acting using the conjugate of z. Good. So C bar is also a complex scalar quantity, i.e. a one-dimensional complex vector space. So we've got now, for any given complex scalar quantity, we're going to have the conjugate of that quantity. A little bit more stuff that's, again, completely standard. So I think, no, we're doing all right for time, I think. So just to note, I mean, so C and C bar, as I say, are both one-dimensional complex vector spaces. That means that they are, of course, isomorphic as vector spaces, but they're not naturally isomorphic. So there's no privileged way of mapping C to C bar. However, what I can also do is take the complex conjugate of C bar, i.e. C bar bar. This, it turns out, is naturally isomorphic to C. So this is sort of like, I mean, this equation is like the algebraic way of expressing it. I mean, this is, but I think the pictorial thing is like a little bit easier. That A is acted on by Z to get taken in this direction. And well, then A bar does the action of Z on A bar is the opposite or the dual or the conjugate of that action. So it takes it to here instead. Well, what's the conjugate of that action? Well, it's just the action that you started with. And so Z, so scalar multiplication kind of acts in C double bar in exactly the same way as it acts in C. Addition is, of course, the same in all three of these spaces. And they have the same underlying set. So you might as well think of C double bar. So C double bar is indeed naturally isomorphic to C, and therefore can be identified with it. Good. So I've now talked about something that we had in the real case, which is tensor products, something we have only in the complex case, conjugation. Then a bit of a question about how those two things interact. I think, I mean, it's not so much that we're running out of time, it's more just that this is slightly tedious reasoning and gives the conclusion that you would expect. So I think I'm just going to skip the conclusion here, which is that roughly that taking tensor products and taking conjugates commute with one another. So if I take a pair of complex scalar quantities, C and D, and I take their tensor product, and then I conjugate that whole thing, that turns out to be the same as taking the conjugate of C, the conjugate of D, and then taking the tensor product of those two. So the conclusion you would really expect to be true. I mean, you have to do some slightly tedious work to kind of justify that thought, but yeah, it's pretty straightforward. I mean, the upshot of it is it's basically very similar to the reasoning that's used here. That one just shows that the way in which complex numbers act on these two one-dimensional complex vector spaces is the same, and moreover, they have the same underlying set. Good. The reason for going through all that palaver is that what that means is that if I now take, so I now am able to get an operation of conjugation that does act on a complex scalar quantity and maps that quantity to itself. The quantity in question is C bar tensor C. So complex conjugate of C, tensor producted with C. And so I've just got the single claim here that if you take this quantity, then its complex conjugate is naturally isomorphic to what you started with. Why is that? Well, so take C bar tensor C and take the complex conjugate of that. That's naturally isomorphic to C double bar tensor C bar because the complex conjugation commutes with taking the tensor product. C double bar we know is naturally isomorphic to C, so we end up getting this. And I mentioned way back at the start that for any two scalar quantities, there's a natural isomorphism between the tensor product of those two quantities and the tensor product of those two quantities in the other direction, in the other order. So what that means is that because I have this natural isomorphism between C bar tensor C and its complex conjugate, then I'm able to define a conjugation map from C bar tensor C to itself. And so that's kind of nice. So that gives me something a little bit more like, so this ends up looking a little bit more like the complex numbers. It's not totally the same as the complex numbers, because even though I have a conjugation map, what I don't have is any way to pick out like unit complex numbers, right? Numbers of unit modulus, for example. So I still don't have like the full structure of the complex numbers, but I've managed to recover conjugation. Good. And so this is then, and this is just the definition of the conjugation map that you get by chaining together these different natural isomorphisms. Good. Now, famously, of course, but so I've mentioned that you do have something that's, you've recovered a bit of the structure of the complex numbers. Obviously, within the complex numbers, you have the real numbers. How does one identify the real numbers within the complex numbers? They're the ones that are invariant under conjugation. And it turns out that you can basically do exactly the same trick. So, or you can do exactly, so you can also ask, well, what are the conjugation invariant elements of C bar tensor C like? So basically, yeah, I mean, I'm not going to go through this. So this is sort of the analysis to justify this claim here. But if you're willing to kind of just take my word for it, then it's going to turn out that R is a full scalar quantity, i.e. a one-dimensional real vector space. And so, yeah, this is, I mean, again, I think sort of what you would expect in some ways, but kind of nice to have it borne out. So I'm going to call this full scalar quantity R the real subspace of C bar tensor C. Good. Moreover, every non-zero. So again, this bit on the right is the algebraic kind of justification of it. But if you trust me enough, then you can ignore that and just pay attention to what's on the left. So that is basically it. So it turns out that every non-zero element of R can be expressed either in the form A bar tensor A or the form negative A bar tensor A. So as it were, the conjugation invariant elements of C bar tensor C are always either basically like conjugate squares or the negative of a conjugate square. So what we'll do is identify the ones of this first form with the positive scale as being positive, and we'll think of these ones as being negative. That is, we'll bestow an orientation on R. And so it'll be a signed scalar quantity. So that means I now can distinguish between its positive and negative cones. Good. Okay, so that's complex scalar quantities. So what I'd like to do now is the final part is talk about intrinsic Hilbert spaces. This is unfortunately the most incomplete part. So this is where we, I don't know, the motorway runs out, kind of, like those cartoons where it runs out halfway across the bridge. But bear with me. So what we're going to do, so I mean, the reason for going through all this palaver is that what we're now able to do is define a notion of inner product that that doesn't appeal to the complex numbers, but rather appeals to this kind of more, reduced version, namely C. So, right, so the kind of the reason you need the complex numbers in thinking about Hilbert spaces is twofold. First of all, that you want to define it as a complex vector space. From my point of view, that's completely fine because the complex multiplication of one element of a Hilbert space in order to yield another element of a Hilbert space is something which is completely invariant under any uniform rescaling of that Hilbert space by an arbitrary complex number. So the fact that H is a complex vector space is kind of fine from my point of view. But the other place where complex numbers, of course, show up is that a Hilbert space is equipped with an inner product, which is, of course, a complex inner product. It takes values in the complex numbers. What it turns out is that you can, in fact, define an inner product as being a map not to the complex numbers, but rather to this thing, C bar tensor C. Yeah, I mean, there's something kind of nice about this insofar as you might think, I don't know, an inner product is, remember, something that's conjugate symmetric. So it's, I don't know, it's got a kind of conjugate character in the first argument, but not in the second argument. And that's, I think, kind of comports fairly naturally with the fact that it ends up taking values in this structure. So yeah, I mean, basically, so this is just the standard definition of an inner product. The point is that this definition is perfectly well formed for an inner product that takes values in C bar tensor C rather than the complex numbers. The conjugate symmetry is fine because, as just discussed, C bar tensor C is equipped with a notion of conjugation. Linearity is fine because C bar tensor C is still a one-dimensional vector space, so I can make sense of this kind of linearity on the right-hand side here. And it's positive definite. What does that mean? That means that for any kind of arbitrary element V in H, then if that element is not equal to 0, then the inner product of V with itself has to be an element of the positive cone of R. So conjugate symmetry guarantees that it will be in this, that V inner product V has to be somewhere in R. Sorry, R not being the real numbers, but rather this real subspace of C bar tensor C. But demanding positive definiteness is a kind of further step. And that's where the fact that R comes equipped with an orientation kind of comes in handy, because otherwise this definition wouldn't make any sense. And then the fact that it's positive definite also means that if V is equal to 0, then we demand that V is equal to 0. In fact, yeah, right. So that's a further demand. But the point is that it turns out you don't need the complex numbers, you just need C bar tensor C. This isn't quite a Hilbert space. This is getting perhaps slightly more into the weeds, but actually, well, no, I think this is also important. So, one of the things that's really important for Hilbert space, of course, is its norm. And so what we're going to do to define the norm of an element V is we're going to say that's an element of R plus to the power of half. So here we're invoking the fact that I can take arbitrary, even fractional powers of positive scalar quantities. And so then we'll define the norm of V as simply being the square root of V inner product V. So V inner product of V lives in R plus, and so the square root of that lives in R plus to the half, using the analysis that we set up earlier. So now that we've defined the norm of an inner product space, we can now characterize a Hilbert space, namely that it's an inner product a complex inner product space which is complete with respect to its norm. And so now we have a characterization of what a Hilbert space is that doesn't appeal to the excess structure of the complex numbers. So now let's just think about a few examples. So just to sort of convince you that this makes sense. So one example is in fact the complex scalar quantity C. That is just a one-dimensional Hilbert space where we define the inner product in the kind of way you would expect. It's just going to be so inner product of A and B is going to be A bar tensor B, which is of course paradigmatically an element of C bar tensor C. Similarly, and then for any for any natural number n, the set of all n-fold sequences in C is going to be an n-dimensional Hilbert space. This would also work if we thought about the set of all maps from an arbitrary n-element set into C. So that is also going to be a n-dimensional Hilbert space. We define the inner product again in sort of the way that seems sort of obvious if you're coming at it from the standard quantum mechanics. And similarly for countable convergent sequences. I think there should also be one even for just kind of capital L2 of C, but I haven't thought about that one in detail yet. So I mean that should work. There's no particularly obvious reason to me why it wouldn't work, but I want to dot my I's and cross my T's before I assert that in a public forum. Good. So, and this is, as I promised, where I unfortunately kind of run out of road. So this is as far as I've got. And so the upshot is that we're able to reformulate the notion of Hilbert space in such a way that inner products take values in a weaker structure. What this means is that physically equivalent states get represented by mathematically equivalent vectors. So, so this is something that's not true of a normal Hilbert space. So if you think about a normal Hilbert space, right, and imagine multiplying everything by, I don't know, 2, then the unit sphere in Hilbert space is going to get mapped to something which isn't the unit sphere in Hilbert space. And in a normal Hilbert space where things take, where the inner product takes values in the complex numbers, that's the unit sphere is mathematically definable. And so multiplying Hilbert space by 2 doesn't count as an automorphism of Hilbert space. If you reformulate Hilbert space in this way, then multiplying by 2, or indeed by any arbitrary complex number, does represent an automorphism of Hilbert space. So this is a way of kind of, as it were, increasing the number of automorphisms of Hilbert space so that there is any arbitrary vector in Hilbert space, it is related to a what I'm looking for, a complex multiple of that vector by an automorphism. Good. And so looking forwards then, the things that I want to do is start continuing to work through this. So it seems to me that these weaker Hilbert spaces should have all the structure that you need in order to do quantum mechanics. But there's a question about kind of making sure that that's true. So, I mean, in broad terms, I think there's kind of 3 directions that I'm playing with as to where to go next. So one is to then kind of build the usual apparatus of linear algebra on top of it. And so, I mean, the definition of an operator goes through completely as normal. The definition of what it is for an operator to be self-adjoint goes through completely fine now that we've got an inner product. And so it's then a question of checking that the things that, and so I expect, though I haven't yet checked it, that a self-adjoint operator will be associated with orthogonal eigenspaces in the way that it is in quantum mechanics, because orthogonality is still well defined in these Hilbert spaces, even though normality, for example, is not. So that's sort of one line of attack. Another would be, so one thing that I would like to do is check the Gleason's theorem is still true for this kind of Hilbert, in this kind of Hilbert space, which again, it seems like it should be, but it would be good to determine that that is indeed the case. And then the third thing that I might want to do is start thinking about C-star algebras rather than Hilbert spaces. And so start thinking about what's going on, trying to use this this is a bit of a warm-up to then think about the perhaps slightly more general apparatus of C-star algebras. So that's kind of where I want to go with that. The other, I think, kind of question that is still standing out to me that worries me a little bit is that, of course, we have another way of getting rid of the complex multiplicative, the excess structure that seems to be involved in arbitrary complex multiplication of a Hilbert space, namely moving to the projective Hilbert space. So that, of course, if you just quotient the Hilbert space by complex multiplication, so you get just the rays, then that also, of course, gets rid of the excess structure. And it does so in some sense in a slightly more powerful way. And so to answer that question, I think I need to think more clearly and deeply about why it is that we don't just always use the projective Hilbert space. I mean, I think part of the answer to that is that projective Hilbert spaces are much more annoying when you're trying to do superposition, because if I have an arbitrary state in Hilbert space, psi, and a state phi, then superposition I define by just doing psi plus phi. Whereas if I have just the ray of psi and the ray of phi, then there's many, many ways to superpose those two rays with one another, because of course psi plus phi is distinct from psi plus I phi, is distinct from psi plus psi minus I phi, is distinct from psi minus phi. So in general, psi plus z phi, where you let z range through the complex numbers, is going to give you kind of different superpositions of psi and phi. It's a little bit weird because that, what I think that's telling us is that given two physically equivalent, two states defined up to physical equivalence, there's not, we often talk about the superposition of two states in quantum mechanics. Really, you actually have a whole bunch of superpositions. You have a whole bunch of ways of superposing two different states. But I mean, I'm not super clear on like how to think about that more clearly. The hope here, I think, is that this kind of apparatus might give us a slightly more insightful way of thinking about what's going on there and how all this relates to superposition. So that is everything that I wanted to say. Here are some references, not all of which are actually relevant to this version of the talk, so let's ignore those. Thank you very much for your attention.
Hi. Thanks, but I see in the chat that Neil can't hear anything.
Sorry, all sorted now, all good. I don't know what was going on, but I did unfortunately miss all the preamble. I could see Jacob presumably explaining the ground rules, but I hope I'll abide by them anyway.
Okay, good. I actually have two questions, and I'm going to ask them both just to get things in here. The first question goes back to the very beginning, where you talk about if we just use the real numbers, we have too much structure. Now, what I'd like to know, and then in a way of example, you talk about, well, we have to talk about in what units things are expressed. Now, unless there's additional structure that is hidden there, and if there is, I'd like to know about it. Why couldn't we just use the Planck units as the natural units and get rid of the arbitrariness in that way? Okay, so that's the first question. The second question is how you deal with spin in quantum mechanics. Because it seems that, well, maybe you don't. Maybe what you need is a value space that corresponds to the integers, whether you're dealing with bosons or fermions. Whether you need some special treatment of that, or whether it just falls out of as a special case of your treatment of a scalar quantity or what. So those are the two questions.
Yeah, good. Okay, those are both really good questions. So let me just make a note. Yeah, so in terms of the first question about just using the Planck units, yeah, I suppose, I guess what I want to say is that, I don't know, fixing on a particular convention doesn't remove a convention, right? So to my mind, I mean, the added structure, I think, would still be there in the sense that for all that you have made a particular choice of convention, you could have made other.
The argument on the other side would be that it is not a convention because it's determined by universal physical constants.
Yeah, so yeah, I'm not sure what to say here, to be honest. So that's something, yeah, that's something I should think about. One thing actually that might be interesting about that is that the one thing I kind of like about this sort of analysis is it also gives you a somewhat nice insight into physical constants. The physical constants start showing up as privileged mappings between distinct quantities. So like Newton's gravitational constant, for example, or I'll do the speed of light because that may be a little easier. You know, it has units meters per second. So it's going to be you can think of it as a privileged mapping between, wait, hang on. Yeah, right. You can think of it as a privileged mapping between the space of lengths and the space of times. And so it gives you kind of a fixed mapping between those. So one thing, right, so I think what I would want to do in order to answer your question properly is, think, well, what are the constants that we're using in defining the Planck scale? And then, I mean, yeah, so is what's going on that those constants then kind of, as it were, chain together a whole bunch of different quantities in a whole loop that allows a fixed identification of all of them with one another, perhaps. But yeah, I mean, I don't know. I at least still have the instinct that there's excess structure in the real numbers. I mean, the reason for thinking that is, partly because you can multiply two. I mean, it's just this sense that you can multiply two real numbers together and get another real number, another thing that lives in that same space. But you can't multiply two masses together to get another mass, something else that lives in that same space. So this extra multiplication operation that the real numbers carry has to be something that a properly intrinsic treatment has to do without. And yeah, I'm not certain then how that's going to relate to the fact that some choices of units do indeed seem physically privileged and seem to get picked out by the constants.
Yeah, well, I mean, it's certainly not going to provide you with, for example, what makes length different from mass, that sort of thing. I mean, that's an additional issue. So I don't see what the real difficulty or what the objection is that product of real numbers is a real number. I mean, you have to multiply the dimensions together of the. I mean, these come not just as raw numbers. I mean, they come as numbers in a particular measurement system, right?
Right. Well, and I mean, that's one way of thinking about what's going on here, is that this is a way of enforcing dimensional analysis scruples. So, it is physically incoherent to add a mass to a length, and so to get a number. But mathematically, of course, you can do that. Like, you can add 2 kilograms to 3 meters to get 5, but that doesn't mean anything physically. And the way we do that in, I mean, one way to do that is to sort of accompany all your numbers by units and use that to kind of keep tabs of what space they're living in. This is sort of another way of doing that, where it becomes mathematically ill-formed to add a mass to a length, because these are now, these are now fully living in different spaces. So yeah, but no, that's good. So I will need to think more carefully about why I don't think that just using the Planck scale justifies the use of the real numbers uniquely.
I have a quick follow-up to this. I don't know, it's not clear to me if this is necessarily helpful, but there's an interesting analogy here between your talk and thinking about gauge theories. So if you're doing, let's say, electromagnetism, right, and you're helping yourself to gauge potentials. One thing you can do to deal with this infinite amount of gauge freedom is to just pick a gauge, right? Pick Coulomb gauge or something like that, and then work with gauge potentials and Coulomb gauge. In principle, if you do enough gauge fixing, you can eliminate all the gauge freedom, and that's one way to go. That seems like homologous to Rob's suggestion of picking a set of units, picking, say, Planck units. Another approach.
I disagree entirely, because picking a gauge in electrodynamics is conventional. I mean, whether you pick Coulomb gauge or Lorentz gauge and so on, there's nothing in nature that picks out one over the other.
Right. Like all analogies, I didn't mean it to be a completely perfect analogy. There is something special about Planckian units, because you're using, constants of nature as opposed to making choices of gauge. Right. That's right. So this wasn't intended to be a perfect analogy, but maybe a helpful way to think about the two ways you could deal with this problem. On the one hand, maybe there's some principled reason to say that one gauge is somehow singled out among all the gauges, maybe not. The other approach is to work with, to define appropriate equivalence classes. So you work with quantities that are insensitive to gauge choice. You reformulate the theory in a sort of manifestly gauge invariant language, and you remove the gauge redundancy, in that seemingly different way. And that seems more akin to what you're doing, Neil, to find a different way to represent quantities, so that we're sort of essentially working with equivalence classes of across different choices. That seems so.
Yeah,
you're right. I don't know that the analogy works perfectly, but anytime you can make at least a metaphorical relationship between two different pictures, you might be able to benefit from some of the intuition you get from another picture.
yeah. So I would say what's being constructed here is in some ways more like it's more like the analog, I think, perhaps of something like the fiber bundle formalism, where rather than maybe you start out with electromagnetism with real valued potentials, and then one thing you could do is move to the electromagnetic fields. Another thing you could do is move to fiber bundles. This is more like moving to fiber bundles in the sense that
Right.
Because you've not kind of identified representations that are related by changing your choice of units. You've rather just made those choices of changing units into isomorphisms effectively is sort of what's going on. But yeah, other than that, I agree. And then, right, so then I think the key question is, exactly as you and Rob were discussing, is the choice of units indeed fully conventional, or do Planck units give us?
I would just argue that
privileged choice of units.
The development of fiber bundles to formulate gauge theories, might not be the only approach to handling a gauge theory, but it's certainly mathematically interesting. And not only mathematically interesting, it's also useful, and also it suggests new things that you can do that you might not have been able to think to do before. So, maybe there's a middle ground here, right? It's not that the availability of a preferred set of units means that there's no purpose in developing another way to work with sort of, manifestly unitless notions of quantity. But maybe it's just an alternative approach. Maybe an alternative approach suggests new things that you can do.
Yeah. Okay. That sounds right. And well, it's very generous. Then so relatively briefly then to respond to Rob's other question. So the other question about spin and I guess discrete quantities more generally. So this is also something that I want to think about more, but I've tried playing with, but I think I feel confused by it. And I think so my worry is sort of the following, that so certainly what I'm naturally inclined to say about spin is that so total spin just has the structure of the natural numbers, and whereas the spin in a particular direction is just going to have the structure of the integers, and that looks like a very natural thing to want to say. The thing that is a bit weird is that we do, part of it is I want to think more carefully about what is going on when we change the unit in which we are measuring spin. So sometimes, like when you're doing foundations quantum mechanics, you just say, oh, I'm going to have my spin values be +1 and -1 for spin up and spin down. Sometimes maybe you set them to be h bar over 2, minus h bar over 2. Sometimes they're +0.5 and -0.5. So we clearly can make choices of what value, and that looks, that in some ways looks a little odd if you're thinking, well, really it's just the structure of -1, 0, and 1. Like, what is it that you're kind of changing then? Maybe that's okay, actually, because really you're just representing them in the real numbers as you would otherwise. But yeah, I don't know. I haven't. Certainly the kind of in some ways discrete quantities are easier because there's sort of like a natural measure on them effectively, so you don't have that complete freedom to kind of scale up and down. But in some ways that makes me a little more puzzled about the right way to think about them. But yeah, that's also, I'm afraid, in the big bucket labeled future work.
Okay, thank you.
Mahmoud had a follow-up on this.
Hey, so this I think Robert has a point here, but I'm not myself, and sorry, I'm at the doctor, so I don't know how you can hear me, but
I hope you're
um,
okay.
okay. Um, I'm not sure how to think about this Planck constant or Planck unit stuff myself, but I'll just, say my little hobby horse thing, which is that, to say that the Planck units are set by nature in a way that other units aren't is sort of making a certain kind of assumption about the constants and their values being fixed by the laws of nature, which I don't think is a trivial metaphysical principle. There's a certain sense in which you can define any quantity as like a ratio of some set of these constants, but there's a certain sense in which we still think of their values as informing what the values of these other quantities are going to be, these other units or just actual real quantities. And so there seems like there might be some conventionality in there depending on how you think about the constants. Yeah, but I do think generally speaking, as people working on this quantity stuff need to look maybe more critically at the notion of conventionality that we're dealing with here, because it seems like there's kind of multiple ideas going on here. I mean, one is just, well, you could just represent it by a different number, but the sort of conventionality that the Planck unit example seems to tell against seems to be a different kind of thing. And it's not clear to me what to say about it, but maybe that's helpful.
Yeah, that is helpful. I think I agree that part of what's going on in the background here is maybe this slightly slippery question about, when is a convention that, thinking about like cases like conventionality to simultaneity, I guess, is like a nice example where it seems it sort of, when you start poking, can become hard to tell the difference between a convention that is much better than all the other possible conventions and something that isn't a convention at all. And that, is something that's something else that I'm in fact also thinking about as it happens, but it's not entirely clear to me how they're going to connect up, but maybe they will at some point.
Right, thanks a lot. So our next question is Eddie. Eddie, please go ahead.
All right, thank you, Neil, for the interesting talk. Learned a lot. I was wondering about two issues that are related. One is, we can separate, as you mentioned, the intrinsicalist vision of getting to the bottom structure of the world from the nominalistic vision of getting to such a bottom level without any numbers or functional sets, right? And I was thinking about your project as situated in the intrinsicalist part, giving us something that's without convention or maybe gauge-free in some way. But do you think can be extended for a nominalist to interpret this project as giving us a picture of the world without mathematical objects too? That is, what is the price to pay to accept your proposal and be also a nominalist? That's the first part.
Yeah, good. So this is something that I also thought about a little bit the other week, although then I stopped because it was clearly going to be a massive rabbit hole that I wasn't going to be able to make any useful progress on. So, trying to think about, right, so so maybe the easiest way to answer it actually is to think about how kind of your version of intrinsic quantum mechanics compares to mine, right? And so here is maybe one way in which one could take the sort of thing I developed here and start develop what looks like a more nominalist version. So this would have to be a version of nominalism that is okay with relations.
Yeah.
But maybe one distinction you could draw is the nominalist is okay with binary relations. So whether they're whether like a certain relation holds between A and B or between A, B, and C and so on. So those are okay. But real valued relations are not going to be okay. So let's imagine a nominalist who is, or and nor are scalar quantity valued relations. So like in my way of doing things, like I'm super happy with the idea that like the distance relations are going to be taking values in some scalar quantity of length. It's just that that space of properties doesn't have as much structure as the real numbers. It has a bit less structure. But so that might be one distinction. The nominalists, as it were, will be okay with binary relations, but they won't be okay with these kinds of relations that take values in some structured space, I suppose, because that commits you to like higher order relations. And maybe those are, I don't know, I don't feel like I fully understand motivations for nominalism. So I sometimes find it a little hard to characterize what nominalists should and shouldn't be okay with. But that seems like a reasonable place to start at least. So, right. So then what you can do is you could say, okay, step one, kind of like what you do, I'm going to fix on the wave function representation rather than trying to think about Hilbert spaces. So with the kind of apparatus I've developed here, a wave function is a map from space to curly C, right? So you can think about it in those terms. I think what you would then need to do is, so now one thing you can do is, as it were, pull, so the structure of curly C is just effectively complex ratios. So you can just like pull that structure down onto the points and say, well, you know, for any 2 points, there's a fact about what their complex ratio is, but that's no good if you're the kind of nominalist I was just describing, who is okay with binary relations but not structure valued relations. So then I think then I think the game becomes a question of saying, well, okay, so can I characterize the structure of curly C purely in terms of binary relations? So can I lay down some binary relations that, you know, just characterize what C is? And that, I mean, this is my way of thinking about what you're doing in your paper, is effectively describing some binary relations that you think will suffice to exactly characterize the structure of curly C. If you do that, then you've got, you know, then, as it were, all the points, so the points of curly C are fully characterized by these binary relations to one another. Sorry, when I say binary, I mean on-off relations. So betweenness, for example, terrible terminology. Betweenness is a binary relation in that sense, and that either betweenness holds between 3 points or it doesn't. It is a three-place binary relation, this terminology. Sorry, that was, and so if you do that, so you have these on-off relations characterized in the structure of curly C, then you pull those relations down to the ground floor. And so then you look at those on-off relations holding between individual points of space. And that then looks like, I mean, that looks more, at least more normal. It's at least a lot closer to the kind of thing Field does in Science Without Numbers. But yeah, that's kind of how I would see going from what I'm doing to what a nominalist might want.
I see. That's helpful. Thank you so much. Kind of just follow up on this. So set aside the nominalist program. What are the main motivations for your project in thinking about intrinsic physics, intrinsic quantum mechanics, and electrostatics, and so on? Is it to do with, say, explanation or parsimony reasoning, or getting a perspicuous picture of the world, or doing just proper ontology, just actually trying to get an honest to God picture of what the world's like?
Yeah, I want to say not really any of those, because I found myself in the slightly awkward position of having, in various places, defended the view that, like, that sort of motivations like metaphysical perspicuity are not things we should really worry about, and that in some sense it's enough to characterize the structure of quantities to just say, look, they're representable by the real numbers, and any two representations related by a rescaling are just as good as one another. Like, so my view is that already in some sense tells you what the structure you need is. I think so. Then this is more about seeing what happens if you try and kind of put that through. So my motivation is, I mean, some of it is, I think, the kind of motivation that Jacob was suggesting. It turns out to be interesting. There's sort of an element of, like, I mean, it's interesting. It's, you know, in the same way that like one-handed sword fighting is like kind of a good exercise. That if you do tie one hand behind your back and you say, look, I'm going to be really rigorous about, you know, what these things are, then you're sort of forced to be more careful about which kinds of equations you're allowed to write down. So for me, like that, I mean, that's part of the motivation, I think, is that it feels to me like it gives me a better sense of, I don't know, like, I feel like I understand inner products better now because I now feel like I understand, which parts of the structure of the complex numbers an inner product actually really makes use of. And that feels to me like it gives me a better understanding of what an inner product space really is.
So it's like understanding or explanation of the
that's probably, it's probably understanding or explanation.
I see.
I mean, I think I would, in general, I'm fairly pluralist about these things though. So I'm also very inclined to think that, I mean, the usual way of doing things also gives you insight and understanding. So I basically think that understanding and explanation come from doing the same thing in a bunch of different ways, rather than there being one way of doing it that generates the most understanding and explanation.
So taking brute quotienting can also give you some understanding in terms of projective perspectives.
I would think so. And I mean, I suppose one answer to the question, like, why am I doing this, is that, I don't know, take your favorite motivation for coordinate-free geometry and apply it here. So some people will certainly want to think of that in terms of metaphysical perspicuity. Some of them, so Jill North, for example, will say that it's because this gives you better insight into the structure of the world. I'm more skeptical of that, but I do think that it gives you some understanding and insight that you don't get from just doing coordinate-based geometry.
I see. That's very helpful. Thank you, Neil.
You're welcome. Yeah, thank you. And thanks for your paper, because that was very helpful in in my own thinking about this, as you can tell.
Oh, thanks. Very kind of you.
Thanks, Eddie. Ben, you're up next.
Thanks, Neil, for the talk. Okay, I have like I have two questions, I guess, and both are about, I think, different directions that make more sense to me for the intrinsicalist project. So the first one is, I mean, the thing that you're building up to is providing an intrinsic characterization of Hilbert spaces and wave functions. But this to me seems kind of strange, because a wave function is a mathematical representation of a state and not a quantity. And as you said, what you ultimately want are operators, which represent quantities. And the intrinsic values that you're describing would presumably be eigenvalues or the spectrum of an operator. And it seems to me like there's a more direct way to get there, which is to try to come up with a theory of algebras of operators over different fields. Because if I understand correctly, your C bar cross C is still a field, right? And I think it's a field that's isomorphic to the complex numbers.
No, it's not going. It's not going to be a field because it doesn't have multiplication. Like, if you multiply an element of C bar tensor C by an element of C bar tensor C, what you get is something in C bar tensor C tensor C bar tensor C.
Okay. Interesting. So it's like you could have like a graded field structure.
Maybe.
Anyway,
because multiplication kicks you from one field up to another is sort of.
Yeah, I think that's what you'd have. But I mean, I was just going to say, it seems more natural to me to actually start by trying to define algebras satisfying something analogous to the C star identity over, I guess, not necessarily a field, but over whatever intrinsic space you think they're taking values in, and to try to prove that you get things like the spectral theorem and the Gelfand representation and the GNS representation. I mean, then you could deal with kind of classical stuff and quantum stuff in one fell swoop.
Right.
And it would also go some way, I think, towards answering, if you can build a theory that's analogous to the theory of C star algebras, you would go some way towards answering Rob's question about spin, because that comes up in terms of representations of operator algebras.
Right.
So I think those quantities would end up just being, things that fall out as the spectrum of certain operators. Okay, but it's a little bit strange if you don't even have a field structure. So how you go?
Yeah, I mean, the thing that's so I mean, there's a sense of which, I mean, I agree. I'd like to try and figure out what this looks like. Part of the problem is that it's sort of this slightly odd thing where I kind of wonder whether working with C-star algebras might in some ways be easier than working with Hilbert spaces, because they've already sort of dispensed with certain amounts of surplus structure. And the thing that is weird to me about C-star algebras, I mean, is that because of C-star algebra, you're allowed to, so if we're thinking of the elements of the C-star algebra as representing quantities, and one thing you can basically always do is add them together. And in some ways, the scalar multiplication, at least the real scalar multiplication on C-star algebra, makes total sense. That's sort of obvious. Of course, there's a quantity of momentum, there's a quantity of double momentum, which is just twice the momentum or something. But one thing that is kind of weird about C-star algebra is that you're allowed to just add arbitrary elements together. And if you've got, one quantity, if you've got position and momentum in the same C-star algebra, then that sum doesn't make any sense. So it seems to me that we're going to want to strip out a lot of the structure of a C-star algebra. And that might, I mean, weirdly, it's the addition structure here that's causing the problem, not the multiplication structure.
So okay, this is my second question. I mean, I've always thought about the spectral values you get within a C-star algebra as values of your quantities within a fixed system of units. So this is going back to the earlier discussion about whether you got a convention or not. And so if you fix a system of units, then just like you said, you've got numbers that you can add and you can multiply and whatever. But so here's something I actually worry about is that maybe there's kind of two ways to put it. So one, I think this analogy that you made to the fiber bundle formalism is not the most perspicuous in some ways. So I can say why. But here's what I worry about is that actually the intrinsic formulation of values that you're giving forgets really important physical structure that's encoded in how quantities change under rescalings of units. So for example, I think this structure plays a role if you're looking at scaling limits in a variety of theories. So think about the Newtonian limit of GR. You want to have, if you take Sam Fletcher's account, you want to have a formulation of GR in which you can think about how quantities change under changes of units. And if, I have this stuff on the classical limit of quantum mechanics where I say the same thing, I think the same thing applies to scaling limits of quantum field theories. So definitions of effective field theories. But so anyway, I mean, we could talk about that more, but I guess what I'd say is in your account, you said all of the unit changes would become isomorphisms, but that's not exactly right. If I understood correctly, all the unit changes would become the identity transformation. And that's not what happens in the fiber bundle formalism at all, right? You still have non-trivial isomorphisms of a fiber bundle. So what I was going to suggest is actually the way to think about change the unit, at least, okay, if you're coming along with me and you want to, talk about somehow giving an intrinsic definition of C-star algebras, maybe, then there are these things called bundles of C-star algebras, which I think can be used to encode this scaling structure, but it's non-trivial scaling structure. And then the unit changes, I think, can be represented as morphisms of the entire structure that aren't necessarily the identity transformation. So anyway, I mean, tell me if I'm getting it wrong, but I think if your value spaces don't involve units at all, then all the unit changes would be the identity on the value space, and that's more like a category theoretic quotient, I guess, which is not how you construct a fiber bundle.
Yeah, good. So I mean, so I agree that whether it's analogous to fiber bundles turns on, whether it's rescalings are to be thought of as the identity. I mean, here's the sense in which I don't think that it's not the identity, is, take the space of mass values. There's a well-defined operation on that, which is like, it maps every mass to twice that mass value. So that kind of rescaling operation acts on the whole space. And I mean, it's not the identity in that it doesn't map points to themselves.
But
so that's the sense in which it maps the whole collective. It maps the whole, if I start out with this space and I apply this double the mass map thing, then what I get is, that same space back again. But I mean, that's true of any automorphism.
Okay, so maybe I'm misunderstanding. So I thought the things that we're worried about are maps representing unit changes. And so the thing I was thinking about was that maps representing unit changes would all become the identity map. But if you're actually, if you're doubling masses and you're not thinking of that as a unit,
sorry,
then there could be non-trivial automorphism.
Okay, good. So then a unit change. Yeah, I suppose it's just that, I mean, I don't know that I want to say that like the maps corresponding to, so yeah, let me think about this. Right. Okay. So this might be what you mean, that like, if I take the mass, so I've got, like, as it were, my mass space, and then I have, let's imagine 2 copies of the real numbers and 2 maps onto the mass space. One is the kilogram map, one is the pounds map. There's obviously there's a multiply by 2.2 map linking those two. And in some sense, in moving from the real numbers to mass, that multiply by 2.2 map gets converted into the identity, as it were. Right. So I agree that happens. I suppose, okay, so the point about scaling is super, super interesting, and that is not a connection that I thought of. And so that's something that I would really like to think about. One thing that has always struck me as like kind of weird about these is, because you're taking a certain limit. So I can't speak to the kind of the quantum case because I just don't know that stuff well. But in the say going from like a relativistic theory to Newtonian theory, there's sort of this slightly weird phenomenon, right, where no matter how big you make C, you get a theory that is kind of isomorphic to what you started with, and so it's related to that original theory by just changing your choice of units. And so you can like dial up C arbitrarily high, and you, in some sense, don't go anywhere. But you get this then qualitative shift when C hits infinity, as it were, where you do now get like a qualitatively different theory. My guess would be, sort of, assuming that something might similarly be true in the quantum to classical limit. So like you start off with your quantum theory, each value of H bar gives you, as you make H bar smaller and smaller, you keep getting, is this sort of slightly, so all of these theories are isomorphic, but in some sense, you're setting up a kind of collection of relations between them, such that then when you take the limit of that and H bar finally hits 0, you do get a qualitative shift. So I don't know. I think that this should work, perhaps, because although any, as it were, finite change to the units doesn't affect the theory on this setup, right? The qualitative shift where you multiply your units by 0 or by infinity, depending on which of these limits you're thinking about, that at least there's the potential for that to be different. But yeah, the worry is that you're going to lose the fact that the sense in which this is indeed an infinite limit or a zero limit. Yeah, good. Okay, I need an answer to that, and I don't know what it is.
I have a quick follow-up question, and I also have a longer question, but I'm going to put myself at the end of the queue because there's some more questions. But so this may be a really naive question, and maybe it's just because I'm not super familiar with Sam's proposal about this, but there seems to be a conceptual distinction between changing one system of units and actually rescaling. So like in a QFT, if you want to study, the normalization group, you want to study effective field theories, we don't do that by changing our units. We actually keep our system of units and we just formally rescale. And the rescaling is, it corresponds to some physical change in our experimental setup. We pump more physical energy into the experiment, or we increase the physical resolution of our optical apparatus, whatever it is that we're doing, whether it's, particle physics or condensed matter. And to me, I don't see how you can even talk about intertheoretic reduction through changes of systems of units. I know that there's this formal process of like taking h bar to infinity or taking taking h bar to 0, taking c to infinity. But I've always understood that to be just a shorthand for, rescaling your, experimental energy scales or length scales, right? You talk about systems that are physically large in space or involve very large energies. And this actually leads into another question I'm going to put at the end of the queue because it's a deeper, more general question about mathematical versus empirical equivalence. But I guess I just need to get a little clearer on, sure, I think in your proposal, Neil, you are saying that changing a system of units is not just an automorphism, but it's actually the identity. It doesn't change any of the quantities of the problem, but you can still help yourself to rescalings. And to me, it seems like it's enough. I don't think anyone in physics is saying we can accomplish something by changing our units. I think most physicists regard that as really a trivial change, something that should, I guess, in naturally in your intrinsic formulation does become trivial.
Yeah, that's
Ben, if I'm misunderstanding this, I'd like to, if you could clarify, because I may just be misunderstanding something.
Oh, I just disagree with you about a lot of that stuff, but this isn't the time to talk about it. So I was going to say in the chat that Neil, we should just talk about this stuff separately because to
be clear, I wasn't trying to make this was really a question. What am I missing here? So I don't know if I wasn't making an argument as much as a plea.
Yeah.
Well, I just don't want to take up more of the time here, but Jacob, we can also talk separately too.
I'd like to do it very much. I'd love to hear more. Mock and Dave, please go ahead. Oh, I'm sorry, Neil, unless you had to follow. Yeah, please.
No, just, I mean, this is basically just to say that I also agree with this point about wanting to say something more interesting about spectral values, because that's sort of the other, in some senses, orthogonal to what I was doing here, because like that's the problem of, how can eigenvalues not be numbers in some sense? I mean, we're like, that's one way of thinking about what's going on there, which it feels like they should be. Like, if a position operator, it shouldn't take numbers as eigenvalues. That's nuts. I mean, space isn't, points of space aren't triples of numbers. It doesn't make any sense. So, but how do you get around that? But again, I'm not sure the best way to do that. But I think I might take your suggestion to make thinking about C-star algebra as the next port of call for this stuff. Yeah, anyway, sorry, thanks.
Thanks. Mock and Dave, please go ahead.
Yeah, I actually, in the same line as Jacob, I was going to ask for some quick lines of clarification because I am very, very unfamiliar with similar work. The first, which I hope will be relatively easy, was could you kind of highlight what the advantage of your proposal is over using just complex projective spaces to talk about wave functions? Because I know they don't describe them in like very initial discussions of quantum mechanics, but I've always been very comfortable with them. It's like, yeah, you can have multiplication and that kind of just shifts an orientation of array. And yeah, that means you don't necessarily have a preferred basis you could construct the same ray out of, multiples of a bunch of different other ones. But there are all sorts of problems in quantum mechanics where you don't have a preferred basis, and I'm kind of okay with that. If you're talking about ontologically, you should have one, then that's another question. But as like a mathematical description, I'm not sure what that is, or what the advantage here is. I honestly just I think I'm missing something.
Yeah. No, I don't think you are. I think, I mean, this is sort of the thing that I said at the end. I mean, part of what happened here is that like I got really drawn in. I mean, this is maybe the drawback to part of this being kind of motivated by interest, that I got super drawn into this question of, what does a Hilbert space look like if you want multiplication by complex scalars, by complex numbers, to be an automorphism of the space? So I kind of built that thing, and then kind of having done that, was a bit like, wait, is this just a like less good way of doing things than projective Hilbert space? As I mentioned toward the end, I suspect that the answer is going to come in. I'm trying to think of the best way of putting this. I suspect the answer will come in when you start thinking about superposition, and perhaps combining systems. So like that part I'm less sure about. But if I want to take a superposition of two states, then I mean, so one thought I think is kind of what I was saying at the end, that if I've just got the two rays, there's actually a whole bunch of ways to superpose those two rays to get a third. So maybe the superposition structure is a bit less clear. I mean, there's kind of a more general background here, which,
Sorry, could I ask for a little bit more clarification on the, how you could make a bunch of different superpositions? Because, you can have lots of different superpositions that give you the same observables, and that's, that is in the end what you look for. And in the same way, you can weight the different rays with a bunch of different ways. But I think that ambiguity, I think, pans out with the observables in the same way. So especially if you want to isolate something that's unique here, I'm not quite sure what the advantage is. And again, very much not sure. Just
no, no, definitely the spirit in which I'm taking the question. So for example, if I've got spin up and spin down, then obviously spin down and negative spin down correspond to the same ray, but spin up plus spin down and spin up minus spin down do not, right? They correspond to different rays. So as it were, I've got my spin up ray and my spin down ray. One way I can combine them gives me the ray including spin up plus spin down. Another way of combining them will give me the ray including spin up minus spin down. So I have these I mean, again, I think there's like something quite nice about that, because what it sort of makes vivid to you is that superposition is in fact a non-unique operation. At least that's my first impression. And so that's actually kind of maybe a useful thing to appreciate, that actually, if you're thinking about the physical states, not the mathematical states, there's a bunch of ways of superposing two physical states with one another to get a third physical state. That said, and so then I think the answer as to why you might want a formalism more like the one I've sketched today rather than projective Hilbert space is, you might say, okay, cool, that's a good and important lesson, but it's kind of a pain to have to keep track of all these, many different superposition operations effectively, or many different ways of superposing states together. So it would be nice if I can, as it were. So now imagine what I do is I take my physical state and I make a bunch of copies of it, where the copies basically, each copy comes with instructions on how to superpose it with another state. So now when I I've got my, as it were, physical state A and physical state B. And the advantage now is that, I pick one representative of each of those, but now I have the instructions on how to superpose them. That would be the advantage of this kind of setup over the projected Hilbert space. Does that make sense?
I think I might still be a little confused, but again, I think that's mostly me. In the interest of time, I might push on to a tiny point and then let others jump in. I thought one thing that was very interesting, but seemed to be like a split discussion, was you had your conversation on, describing the wave function and constructing your own formalism there. But if you're just talking about the wave function, unless you've already chosen, a system or observables you're looking at, you don't really have units that you're looking at when you're discussing the I mean, you also even have to specify like what dimensional space you're working in. But when you start discussing observables and the operators where you actually observe things, then I can see the discussion about, shifting units that seem to be the motivating factor at the beginning, playing a much more direct role. I got a bit lost at how that connected when we started talking about wave functions and then just scaling things, all these different operations on C. So because I'm unfamiliar, I think it seems as though there's kind of two different discussions. One just going on about the like mathematical structure of, the states that we use to describe, or how we describe states in quantum mechanics, and another describing how we obtain quantities from those states, and the ambiguity in giving those quantities meaning or giving them how we can fluctuate from one system of units to another.
Right.
So that was a question, is whether that split was one, or was something, again, a misunderstanding?
No, I think that split is there, and I think so. And then the motivation, I suppose, is sort of there's a similarity of motivation, which is that in the same way that we don't think that at least passive rescalings of values change the physics. We also don't think that complex multiplication of the states changes the physics. So, there's a kind of, I think in some sense, these are two conceptually distinct projects, but with a sort of analogous motivation. Right. Part of the reason for kind of combining or doing them together is also that, a lot of the apparatus looks pretty similar. So partly that having kind of thought about this stuff for the case of real quantities, then thinking about it for, moving over to the complex case was relatively easy to do. And then the third, and then I do wonder if these might come together, when, for example, one's thinking about algebras of quantities, whether I suspect that, like at least one thing you're going to want to do is kind of not necessarily have the full structure of the complex numbers running around in your algebra of quantities, as it were. This is going back to the conversation with Ben, and that might already give you some clues as to how to make your observables that are the elements of the algebra take values in like an intrinsic space rather than just the real numbers, or the real numbers raised to some Cartesian product of the real numbers, Cartesian power. But basically your instinct that these two things are kind of separate, I think is right.
No, I really appreciate that. I'll stop here because I know Jacob might want to ask a question, and Eddie still has his hand up. So thank you.
Right. Yeah. Thank you.
Thanks, Makinde. Eddie, why don't you go first? If I run out of time, it's okay.
All right. Thanks. So I was wondering about this connection that's not often discussed, which is the Intrinsic program and in flutter physics and foundation physics, and the shape space program pioneered by Julian Barber collaborators. And there's some connection regarding intrinsic formulations, although, for shape space, they are using a lot of quotienting by hand. Yeah. So it's hard to get to the bottom of what shape space looks like in intrinsic list terms. And recently, there's a very nice paper by Dewar Nino Zangi and Shelley Goldstein, extending the shape space dynamics to a quantum case, motion
right.
of shape space in Bowen mechanics. So they show that how, actually, I'm going to send the archive link, paper, I think it's probably in General Statistical Physics 2019. And they show that how the relational structure on shape space and the metrical structure on shape space allows you to define this gauge-dependent emergence of dynamics for particle motion in quantum mechanics. So that's something to explore, I think, for lovers of the intrinsicalist idea. And I'm not exactly sure what the connections are, but I think it can be a fruitful area to look at.
Yeah, good. Yeah, that sounds interesting. Yeah, that sounds super interesting. Yeah, good. So maybe, I mean, one thing that is right. So one connection here, I guess, is that I mean, this is totally off the top of my head, so this isn't a connection that I've thought of before, but yeah, so I think I'm right in saying that in shape dynamics, just rescaling, so length rescalings are automorphisms off the bat, as it were, which of course isn't true in normal Newtonian physics. So if I rescale length without, unless I also rescale mass and time, then I don't preserve the equations of motion. Whereas I believe the shape space equations are indeed invariant under arbitrary length rescalings. Is that right?
Yeah. So you have Bass matching principles. Right. You have this dynamics on shape space, but it can be lifted into the absolute space time, where you can talk about length and various other gauge-dependent degrees of freedom. Yeah. So I suppose one thing, I mean, right. So it might just be that one thing that the kind of stuff I've been sketching here could be interesting for would be a certain perspective on what it is that makes shape dynamics different to Newtonian mechanics. Yeah. And I mean, again, this is off the bat, but my suspicion is that it's going to turn out to be that shape dynamics doesn't have constants of nature, right? So if you have this sort of intrinsicalist version of Newtonian mechanics kind of been discussing here, then why is it then, if you rescale length, the thing that forces you to rescale time and mass is basically that all of these quantities are kind of yoked together by effectively by Newton's gravitational constant. Yeah. So that's what kind of yokes distinct quantities to one another. Yeah. And then, so, in some sense, then it's going to be that what's going on in a program like ShapeSpace is that the length quantity isn't yoked to any other quantity. And so arbitrary rescalings of that quantity can be made without needing to make any corresponding or compensating adjustments to any other quantity. So there definitely, I think, should be a lot more freedom in shape space. Yeah. Speaking there. Oh yeah, there definitely is. Yeah. General physics. And also metrical time becomes something that's going to be relational and non-fundamental. Yeah, right. So, and in the quantum case, in the paper by Dewar and co-authors, it turns out that even potentials, interactions, or the form of Schrodinger equation are gauge dependent. So a lot more things turn out to be gauge or conventional from this perspective than on traditional view of physics, namely that we think that there are some fundamental things like forces, interactions, potentials that make things move. But on this picture, they're all gauge. They're all choices of gauge of describing this shape path in shape space. So it is in the same intrinsic spirit, but it is in some sense more radical, in some sense more conservative. In more radical sense that many more things are intrinsic, and more conservative in the sense that I don't think they have attempted the honest to God kind of intrinsicalist formulation because they rely on quotienting. Right, interesting.
We're going to have to close it there. So thanks again. I want to thank Neil again for an amazing talk and for leading a wonderful Q&A. And thanks to everybody for being here.